Alright, in this video, we're going to focus on a little bit more of what's going on behind the spectral lines that we first talked about in the previous lecture video. So we're going to cover sections 5.4 and 5.5 out of the Openstax Astronomy chapter 5 in this video. And it's going to focus on a little bit of chemistry from high school chemistry that we'll just refresh ourselves and make sure we're all on the same page. And then talk about what astronomers are actually learning from the light that they receive and those spectral lines that seem to be missing in a star's absorption spectrum. So this slide is fully information that should have been presented to you in a high school chemistry class, but not everyone has the same high school background, and not everyone has had high school as recently as their peers. And so this is going to be a just refresher of that key information that we should know before we move forward. So when we talk about an atom, we're talking about the smallest piece of matter that we can really think of. We are composed of atoms, and what we're going to learn is that even though we feel very solid, we're actually mostly empty space, because an atom has two main parts. There's the nucleus, the tiny inner piece that has most of the mass of the atom, and that's where we have protons and neutrons. Now, protons have a positive charge, which means the nucleus has an overall net positive charge, and neutrons don't have an electric charge, they just kind of provide mass. And then the other key part of an atom is the electron cloud. So electrons kind of move around the nucleus. They don't quite orbit the way that planets do, but they are found away from the nucleus, some distance away. And an atom is mostly empty space because in between the nucleus and the electron cloud is literally nothing. There is no mass, there's no material in between that tiny nucleus and that electron cloud. And the picture on our slide is meant to give us a small sense of the relative sizes, because the nucleus is like we had a tiny little grape seed and we put it down in the middle of a football field. And that football field wouldn't even stretch all the way to the electron cloud. That's how much empty space there is between that small, dense nucleus and the electron cloud around it. Now, atoms are the smallest possible sample of a chemical element, and we're going to have to get a little bit used to the periodic table, which you would have seen in a chemistry course in K through 12. But the main thing is that when we look at a periodic table, it has some pieces of information for each chemical element. The most well-known and obvious piece of information on that element, besides its name, is the atomic number. That number, 1 for hydrogen, 2 for helium, and so on, is actually telling us how many protons are in the nucleus, because by definition, that number of protons determines what we're actually calling that atom. So hydrogen has 1 proton. No matter how many neutrons it has, 1 proton means hydrogen, 2 protons means helium. A couple of other elements that we're going to see fairly commonly are carbon, which has 6 protons, and so on the periodic table would be the atomic number 6. And oxygen has 8 protons, the atomic number 8. If we looked further at the periodic table, often what is also going to be in that little box, besides the name and the chemical element and that symbol, what letters are used to represent that element name, there's usually also a mass number, and what's there is usually the most common mass that atom has in units of hydrogen, in units of protons and neutrons. So the nucleus of an atom also contains neutrons, and the number of neutrons determines the version of that atom. The idea of different versions of the same named element is what we call isotopes. So isotopes is just a fancy science way of saying versions. Now on this slide we have two examples. The top, we have hydrogen, 1 proton, 0 neutron. In the top right we have deuterium. Deuterium is actually a fancy name for a version of hydrogen. Since there's still only 1 proton, it still has to be hydrogen. And there's 1 proton and 1 neutron, and so that's hydrogen 2, which is common enough in the universe that we have a special name for it, deuterium. But if you search that whole periodic table for something called deuterium, you won't find it. The second level down, we've got carbon-12 and carbon-13. The idea of carbon comes from the number of protons, 6 protons. And the 12 comes from adding up the protons and the neutrons together. So carbon-12 is 6 protons plus 6 neutrons. And carbon-13 is 6 protons plus 7 neutrons. We don't need to memorize these different isotopes, but we need to recognize that the number of neutrons has meaning when we're thinking about what an atom is and what these different things that we're learning about being part of the atom, what they're trying to represent. Two atoms with the same number of protons but a different number of neutrons are called isotopes, as we said. The proton count tells us the element name, and neutron count tells us the isotope number. The one really important distinction is that most commonly, hydrogen isotopes aren't just called their isotope number, hydrogen 1, hydrogen 2, hydrogen 3, but they actually have different names. So deuterium we saw on the previous slide, and deuterium is part of molecules of heavy water. If you've ever heard that term heavy water, and I think we're going to hear it somewhere off in chapter 16 or something like that. But heavy water is water molecules, H2O, that have deuterium atoms where normally it's just a normal hydrogen 1 isotope. And then tritium is tri for 3. It's hydrogen 3. And tritium is used in a couple of real experiment uses, like lasers. Actually, there's some tritium uses of those. So they're common enough because hydrogen is the most common element in the entire universe, that those elements, those isotopes of the element hydrogen also have special names. We don't have to memorize them, but if we see them, it's useful to know what that word is trying to tell us. Okay, so we've basically made it through section 5.4 already, because 5.4 is really just a refresher on some key chemistry information that we should have seen before this class, but not everyone has the same background. So the number of protons determines the chemical element, where on the periodic table, what name we give that element. And the number of neutrons determines the isotope, or the version, the type of that element. So we've talked about protons and neutrons. What about those electrons? Now, the common chemistry idea about electrons is that it determines the charge of the atom, and that is really important in chemistry. If the number of electrons and protons are equal to each other, we have a neutral atom. But electrons can actually be fairly easily added or removed from an atom around a nucleus. When that happens, the atom is ionized, and it's called an ion. So an atom with too few electrons, if we stole electrons from a neutral atom, it would become a positive ion. There's more protons positive than there are electrons negative. An atom with too many electrons, we added extra electrons to a neutral atom, is a negative ion. There are more electrons negative than there are protons positive. Now, section 5.5, though, actually gets into what else about the electrons astronomers care about. So along with ionization, the movement of electrons to being closer to the nucleus or farther from the nucleus means those electrons are carrying different amounts of energy. This is what astronomers really care about. And an important kind of note here, in this class, in all of astronomy 102 or 103, we will be using a really simple model of an atom called the Bohr model, presented in the textbook. This is much too simple for most other elements. But for hydrogen, it's actually a pretty good approximation, and it's going to be a useful, not to scale, simplified model for our purposes, even extending beyond hydrogen. It is not good enough for chemistry purposes, but for the level that we need our understanding to be at, it's going to be okay for us. So just kind of a caveat to our discussion. In the simple Bohr model, the way that we think of electrons moving around the nucleus is by having a certain distance of its orbit. Now, we're not really supposed to think about the electrons orbiting the way that planets do, but it's going to be an okay thought for us to have in astronomy. It's not true to life, but it's going to be okay for our purposes. Now, those different distances away from the nucleus, the important part is that they have different amounts of energy, and so we call them energy levels. So we just kind of think of those levels as being like a ladder, a set of stairs that the electrons can stand on. And the key point is that each atom is unique in where those levels are. And just like a ladder, you can only put your foot on the actual rungs that exist. You can't set your foot in between two rungs. It'll just drop down to the lower one. Electrons cannot exist at distances separate from these energy levels. Those are the only places that they can be. So each atom has a unique set of energy levels, like fingerprints, and what that means is that each element has a different set of spectral lines. So when we say each atom is unique, I mean each element is unique, like a fingerprint. Okay, so let's think a little bit harder about what's making those spectral lines. This slide has a lot of information, but we'll go through it slowly, and it's worth kind of writing out this information as we cover it. Electrons are able to change energy levels. In order to do that, though, they have to interact with photons. Remember from earlier on in chapter 5, photons are light particles that have wave properties, but photons are pieces of light that carry energy. So we can think of it like giving an electron extra energy, like a Diet Coke or a coffee, and then the electron can jump up to higher energy levels, or the electron can give that energy back and jump back down. So there's two possibilities here. If a photon is absorbed, so imagine drinking that coffee, then the electron all of a sudden has more energy and can jump up to a higher energy level. What we mean by up, we mean further away from the nucleus, a further distance, a bigger energy to that particular energy level. When the electron jumps back down to a lower energy, maybe you provided it with a can of Red Bull, and so it's like, okay, I'm going to do exciting things. And then it's like, no, I actually just want to go back down to lower levels, and it hands it back to you. It gives you that energy back. It emits a photon. So electrons can give off photons if they're dropping to lower levels, or they can receive photons, and then those photons are gone if those electrons then jump up to more energy, higher energy levels. Now, what the big key connection is that because those energy levels are at specific distances from the atom in an energy sense, it means that we have to give the electron the exact right amount of energy that corresponds to wherever it started to wherever it wants to go. Just like rungs on a ladder, we can't put our foot halfway between two rungs, and the electron can't make change. We need to give it the exact right amount of energy to move one step, or more energy, but the exact right amount to move two steps, or so on. If there's the wrong energy, then the electron just doesn't interact with that photon at all and just lets that photon pass it by. But if it is the right energy, then it will absorb that photon and jump up to the higher energy level. But another really key idea for us is that electrons are really lazy. Electrons want to just sit on the couch in the lowest possible energy level all of the time. So if you give that electron some coffee and you're like, let's go do an exciting thing, it'll jump up to that higher energy level because you provided it with energy. So from an outside source, we gave it energy. But at any point, once the electron's up and excited and ready to go, it can decide, no, I actually want to go sit back down on the couch. It can drop back down and emit that photon. It doesn't require an external source of energy to jump back down to lower levels. So a couple of key terms for us that are going to come up over and over. An atom with any amount of electrons, one or more electrons in an upper energy level, basically electrons that are off the couch doing exciting things, that atom is called an excited atom. But atoms do not stay in the excited state because those electrons are lazy. The electrons want to jump back down to the ground state, the lowest possible level. So that other term on our slide here, ground state, is the lowest possible level the electrons are allowed to be. The electrons are never in the nucleus, but the closest that they can get is called the ground state. That's the couch. Electrons always want to be in that lowest energy state. And so if you give them energy to jump back up, it won't take very long for them to jump back down again. Okay, so let's push our critical thinking a little bit. Hydrogen as an atom. Hydrogen atoms can produce a specific set of visible light spectral lines based on all the transitions from higher energy levels down to what's called the n=2 state. Now something key here. n=1, the smallest circle here that's drawn, is still not in the nucleus. The nucleus would be a tiny, tiny dot right in the middle of this picture. n=1 is the ground state. And so what we're looking at with our little colored arrows here, red, blue, green, and violet, are jumps from higher energy levels to n=2. So imagine that we're in like a 5-story building, okay? The lobby's really where we want to be. These levels are saying we were on the 3rd floor, we went down to the 2nd, or the 4th floor and we went down to the 2nd, or the 5th floor and we went down to the 2nd. It's those particular jumps that happen to be the right amount of energy that when we look at what wavelength that amount of energy corresponds to, it's in the visible part of our electromagnetic spectrum. This is called the Balmer series. We don't have to memorize that. But something for us to think about briefly. So I'm going to pose the question and then I'd like you to pause. It doesn't say to, but I'd like you to pause and think about the question. There's a different set of lines that go all the way down to n=1, to the ground state. So from 2 to 1, from 3 to 1, from 4 to 1, from 5 to 1. They were discovered after the set shown here because they're not in the visible light range. Those bigger jumps from the 5th floor all the way down to the lobby, 4th floor all the way down to the lobby, are those bigger jumps going to be in the infrared or in the ultraviolet? So think about that. Rewind if you have to re-listen to the question. But that all of the transitions down to n=1 are called the Lyman series, Lyman. We don't need to know the name, but if you're curious. And are those going to be mostly in the ultraviolet or the infrared? Since they're not in the visible, these are the key spectral lines that we're already looking at are the ones in the visible. So pause and think. All right, the key is that bigger jumps mean bigger amounts of energy. And so if we think about ultraviolet light compared to infrared light, the one with more energy than visible light is the ultraviolet, right? We wear sunscreen because that higher energy is dangerous. We're making infrared light all the time, not dangerous. So transitions to the n=1 stage, the Lyman series. We don't need to know the name. Bigger jumps mean more energy. That is a key idea. Bigger jumps mean more energy. Okay, a pause and think question for us, because this upcoming lecture tutorial that you're going to do in a bit, or after you have talked through the, or thought through these slides, and then we'll do it, if you're in the flipped classroom, we'll do it in the next on-campus lecture that we have. A pause and think question for us. Energy is released from atoms in the form of light when electrons do what? So pause and think through and read through all the options. Okay. Hopefully, when we went through some critical thinking and ruled out ones that we knew were definitely wrong, hopefully we narrowed it down. And the first thing that we ruled out was number 2. Moving around the nucleus isn't really supposed to be part of the model of an atom at all. So moving around compared to towards the nucleus, closer distances or farther away. So 2 we should have ruled out right away. If we are releasing energy, we definitely aren't talking about absorption of any kind. So 5 we also should have thrown out right away. Now, 4 is a common wrong answer if we read through the question and options too quickly. When energy is released, what is the thing being emitted? Because it isn't electrons. Right, it's the photons. The pieces of light, the light particles, are the things being emitted, not the electrons. So 4 is also incorrect. So if we're trying to get rid of energy, that means the electron's trying to get back down to the couch. It was at a higher energy level and it dropped back down to a lower energy level. So option 1 here is the correct option. If you voted 3, then you at least kind of narrowed down to remembering that it's electron movement, but it may actually be worth rewinding and watching a little bit more of this video again so that it really starts to click what direction we mean. And think about those electrons sitting on the couch not wanting to do anything, and you're forcing them to walk upstairs. All right, so now would be the right time to try the lecture tutorial Light and Atoms on page 65 through 69. And one thing to note, even our textbook is not careful with the proper way of drawing atoms. It's actually something that's important to recognize when we see a correct drawing, but it's not something we focus on the details, the physics behind why. But when we look at these 2 student drawings, and there's going to be a discussion between those students that basically comes down to, well, the teacher said this, and the other student says, no, I think the teacher said that. Like, they don't even describe their thinking, because we don't get into it in this course. But student 2 has the correct drawing here. One important thing that we're going to see as we move further in our applications of these ideas to science is that there's bigger gaps near the ground state. So the biggest jump is from the ground state to the next level up, n=2. And the gaps just get smaller and smaller as you go out. We won't get into why that is, and we won't really worry too much because we're not doing any of the calculations that rely on that. But student 2 is the right drawing, and we won't worry about that question in the lecture tutorial. This set of atoms, A, B, C, D, E, and F, are ones that page of the lecture tutorial that asks questions about which one's emitting or absorbing the different colors of light. That is a really, really good check of our critical thinking skills. And we'll go through it together in either online office hours or in class. But I really want to make sure you try that because it is a good check to see if things are clicking with us in this section and the previous sections. right, a pause and think question for us once we finish the lecture tutorial, but we might even have a sense of it now. If the electron in atom B here is moving from an energy level amount of 3 to an energy level amount of 6, what is happening in that atom? So pause and think through. All right, we're going from the ground state in B, we're sitting on the couch, and we're jumping up to a higher energy level, which means we had to give that electron some energy. We had to bring it a coffee or a Red Bull or something. That means that a photon had to be absorbed, right? We had to drink the Red Bull. And so our only options here are 3 and 4 because they have absorption. And the amount of difference, we jumped from 3 to 6, that gap of 3 is the amount of energy we need. We need that exact amount of energy. So option 3 here, a photon of energy 3 is absorbed, is the correct one. We don't need to know the units, and we don't need to worry about more complex calculations than that. But that is the heart of our understanding of what we mean by absorbing and emitting energy in the form of photons. So, this slide is one of the big connections between the previous video, thinking about blackbody radiation and spectral curves and emission spectrum and absorption spectrum, and our newfound understanding of what's happening at the atomic level. If we look at that source on the far left of the source of continuous spectrum, we think about that as like a filament light bulb. It is just a hot, dense object that is glowing. That piece of metal in the light bulb is glowing. And if we were to look directly at that light bulb and sort out all of the light into a spectrum, we would see a continuous spectrum. It would be a blackbody curve, and it would be a continuous spectrum. If that light, though, passes through a cloud of gas, our new understanding is that that light contains a whole bunch of different photons, some of which correspond to the right jumps from the ground state to the n equals 2, or ground state to n equals 3, or ground state to n equals 4, or from 2 to 3, 2 to 4. All those different jumps in the ladder correspond to specific wavelengths that those atoms are going to steal as the electron absorbs those in order to jump up. But the electrons are lazy. They want to jump back down. And so if we're just looking at that cloud of gas and we don't see the light bulb at all, we'll see a whole bunch of atoms that are excited atoms that the electrons, being lazy, they want to jump back down to lower levels, and they emit the same ranges, the same wavelengths that they stole in the first place, because whether we're jumping up or down, the gap is the same amount. And so we end up producing spectral lines because those are the only photons available to be emitted by that particular group of atoms. What that means is we can look at which wavelengths are being absorbed if we're looking through the gas at a continuous source, or what wavelengths are being emitted if we're looking straight at the gas. And that actually tells us what element we're talking about, because, as we said earlier on, every element has a unique fingerprint. The specific gaps in the ladder of energy levels are different depending on what element you have. And so that kind of connection is the one that we want to really solidify between the previous lecture video, thinking about spectroscopy in this general sense, and this lecture video, thinking about what's actually happening at the atomic level. And that's where we're going to kind of finish up this week's worth of content. Because section 5.6 is a whole separate video. Doppler shift is a separate video that we're going to cover in the following week. So in general, in this chapter, we discussed at the very beginning light, what we mean by light, and its more technical name, electromagnetic radiation. We learn about the different types of light, that light acts like a wave. It's got wavelengths and frequencies. and it kind of acts like a particle. Photons are pieces or packets of light waves. And we learned that all forms of light travel at the same speed through space, and the speed of light, c. We then, in the previous video to this, 5.3, and this video, thought a lot more about the actual light that stars give off, which is based on the idea of blackbody radiation that we went through kind of slowly, hopefully. You can always rewatch. And the patterns of spectral lines that are missing tell us about what those stars are made of. What atoms, the specific fingerprints that are present at the scene of the crime, at the star, that are missing. And then the patterns can shift. That statement in our slide here, that's what we're going to focus on in section 5.6. But all of chapter 5 is a really important baseline for us to understand how astronomers get all of the information that we do about stars, because it's all based on the light we receive. We can't go visit those stars. We can only gather the light that they're producing. So that's where we're going to finish for today and for the week's worth of content. But we are going to really dive into those lecture tutorials that I've been talking about, and other activities that will hopefully help solidify some of these ideas, because they are really important ideas, but they are also difficult ideas. Chapter 5 is the longest and most important part of our semester per chapter, because our understanding of chapter 5 is going to continue to help us as we move forward through the rest of this semester. So that's where I'll leave us for today.